March 27, 1943. Luftwaffe Fighter Control Center, Diemen Air Base, Netherlands. Major Hajo Herman stared at the illuminated situation map, watching red markers representing RAF bomber formations materialize across the North Sea. Each marker represented approximately 30 to 50 aircraft, their positions updated every 3 to 5 minutes by the Freya and Würzburg radar stations dotting the Dutch coast. Herman, architect of the Wild Saw night fighter tactics and holder of the Knight's Cross with oak leaves, had spent 18 months perfecting Germany's radar-guided air defense system. The British bombers flew in loose formations, their positions predictable, their flight paths constrained by weather and geography. German controllers vectored night fighters to within visual range, where experienced pilots completed the intercept. The system worked because the Luftwaffe understood radar's fundamental limitations. It showed where aircraft were, not where they were going. Complex calculation and human judgment bridged that gap. But tonight, something unprecedented appeared on the screens. American bomber formations over the channel, flying in weather that should have grounded them. Solid cloud cover from the surface to 20,000 feet, visibility 0, freezing rain turning to ice above 12,000 feet. Conditions where the most experienced Luftwaffe formation leaders would abort rather than risk mid-air collisions. Yet, the American formations maintained perfect spacing, their bomber boxes geometrically precise through clouds where German pilots couldn't see their own wingtips. Each group of 54 aircraft held formation tighter than Luftwaffe formations flew in clear daylight. The markers on Herman's screen showed spacing so consistent it appeared mechanical, mathematical, impossible. What Herman didn't know, what no Luftwaffe tactical analyst would understand until American wreckage littered French fields in late 1944, was that every single American bomber carried a radar system more sophisticated than anything guiding German night fighters. While Luftwaffe formations relied on visual contact between aircraft, Americans flew blind through weather, their radar sets painting pictures of neighboring bombers, providing positioning data more accurate than human vision could achieve in perfect conditions. The technology the Wehrmacht had dismissed as too complex, too expensive, and tactically irrelevant had transformed American strategic bombing from a fair-weather operation into an all-weather industrial system that would grind Germany's war economy to dust. Luftwaffe intelligence had studied captured B-17 wreckage since August 1942. They found the SCR-521 identification, friend or foe transponder, the SCR-729 radio compass, even early versions of the H-2S ground mapping radar. These discoveries confirmed their assumptions. Americans built heavy, complex electronic systems that added weight without providing decisive tactical advantage. The Freya and Würzburg radars guiding German interceptors weighed several tons, required trucks for transport, and needed extensive ground installations. Miniaturizing such systems for airborne use while maintaining useful range seemed technically impossible. The Americans must be experimenting, testing concepts that would never achieve operational significance. But on that March night in 1943, Herman watched 72 American bombers maintain formation through weather conditions, where 12 German bombers would be considered an achievement. The geometric precision of their spacing, the mathematical consistency of their positioning, the mechanical regularity of their course corrections all suggested something beyond improved training or exceptional skill. Unknown to Herman, 8,000 miles away in Massachusetts, factories were producing airborne radar systems at rates the Luftwaffe deemed impossible, equipping every American bomber with electronics Germany thought existed only in experimental laboratories. Luftwaffe intelligence assigned the systematic failure to understand American radar deployment to Abteilung IC, the the technical intelligence section responsible for analyzing captured enemy equipment. Oberst Joseph Kammhuber, architect of the Kammhuber Line air defense system, personally directed the investigation into American electronic capabilities. According to captured documents preserved in the National Archives Record Group 242, German technical analysis of downed American bombers from August 1942 through March 1943 identified multiple radio and radar systems, but consistently underestimated their operational significance. The first comprehensive analysis, dated September 15, 1942, examined wreckage from a B-17 shot down near Rouen, France. German technicians recovered an SCR-521 transponder, components from the SCR-729 radio compass, and fragments of what they correctly identified as a ground mapping radar system. The report concluded these systems were experimental equipment, unlikely to see widespread deployment due to excessive weight, complexity, and production requirements. The analysis noted that equipping 1,000 bombers with such electronics would require industrial capacity exceeding Germany's entire radar production. Therefore, American electronic equipment represented experimental concepts rather than operational systems. A second assessment, dated January 23, 1943, revised this conclusion after analyzing 12 additional B-17 wrecks. The frequency of radar-equipped aircraft suggested broader deployment than initially assumed. However, the assessment maintained that electronic complexity limited operational effectiveness. The report stated, American electronic systems demonstrate technical sophistication but tactical irrelevance. Complex equipment requires extensive maintenance, breaks frequently, and provides minimal advantage over visual navigation and radio communication. German operational doctrine correctly emphasizes pilot skill and tactical flexibility over electronic dependence. This conclusion reflected German operational experience. Luftwaffe night fighters used Liechtenstein radar for final intercept, but the system's 10-kilometer maximum range and limited reliability meant pilots completed most attacks through visual acquisition. The Würzburg ground radar guided fighters to the general vicinity. Human eyes completed the engagement. German doctrine assumed radar supplemented traditional flying skills rather than replacing them. American formations flying precise patterns through solid clouds suggested either exceptional pilot skill or some capability German analysts hadn't identified. By March 1943, Kammhuber assigned Captain Wilhelm Specht, the Luftwaffe's leading radar specialist, to investigate American formation-keeping capabilities specifically. Specht's team analyzed combat film, interrogated captured American air crews, and studied wreckage from 14 bombers shot down during February and March. Declassified records from the Bundesarchiv Militärarchiv reveal Specht identified the key technology, an aircraft-mounted radar system capable of detecting other aircraft at ranges exceeding 5 kilometers. His report, dated March 30, 1943, concluded this technology existed but questioned its reliability. American claims of radar-guided formation flying appear technically feasible but operationally improbable. Such systems would require miniaturized components, reliable power supplies, and trained operators for every aircraft. Industrial requirements would exceed American production capacity, even assuming unlimited resources. Specht's analysis demonstrated sophisticated understanding of radar technology, but systematic failure to comprehend American industrial capability. He correctly identified that equipping 1,000 bombers with formation-keeping radar would require approximately 2 million electronic components manufactured to precise specifications. He correctly calculated that training operators for such systems would require 6 to 8 months per crewman. He correctly estimated the cost per unit at approximately $10,000. His conclusion that Americans couldn't achieve such production reflected accurate assessment of German industrial capacity, not American capability. The Wehrmacht consistently analyzed American potential through the lens of German limitations. The Luftwaffe devoted substantial resources to solving the mystery. SPEC's technical intelligence section grew to 32 specialists by June 1943. They examined every piece of captured American electronic equipment, attempted to reverse engineer recovered components, and tracked American bomber tactics for patterns revealing radar employment. Nothing worked. American formations continued flying in impossible weather, maintaining impossible spacing, achieving impossible accuracy. German intelligence escalated the problem to Reichsmarschall Hermann Göring personally, who ordered a comprehensive assessment of American electronic warfare capabilities. The resulting report, completed in August 1943, concluded that Americans possess some form of advanced formation-keeping radar, but estimated deployment at fewer than 20% of operational bombers. This estimate, based on analysis of 23 shot-down aircraft, reflected fundamental misunderstanding. The Luftwaffe examined wrecks, found radar equipment in some but not all, and extrapolated from this sample. What they didn't understand was that American airborne radar, unlike German ground systems, could be completely destroyed in crashes. Absence of radar components in wreckage didn't prove absence of radar in the aircraft. By August 1943, virtually every American bomber over Europe carried at least one radar system. The Luftwaffe's 20% estimate missed the reality by a factor of 5. The story began not with bomber crews or radar engineers, but with a test pilot's near-death experience. On October 7, 1941, Major James Doolittle flew a series of instrument landing tests at Wright Field, Ohio. Doolittle, holder of a doctorate in aeronautical engineering from MIT and winner of nearly every aviation trophy in America, had pioneered blind flying techniques throughout the 1930s. The October test examined whether aircraft could maintain formation through clouds using only instruments. Doolittle flew in the rear position of a three-plane formation, following two other aircraft into solid cloud cover. Within 90 seconds of entering clouds, Doolittle lost visual contact with both lead aircraft, despite their separation of only 50 yards. His artificial horizon indicated wings-level flight, but spatial disorientation made him certain the instrument was wrong. Only years of instrument flying experience kept him from entering a fatal spin. After landing, Doolittle wrote a memo to General Henry H. Arnold, Chief of the Army Air Forces. The memo, preserved in the Arnold Papers at the Library of Congress, stated simply, "Formation flying in clouds is impossible using current methods. Aircraft will collide, formations will scatter, and bombing accuracy will become impossible. Without solving this problem, strategic bombing becomes limited to clear weather operations, restricting availability to approximately 30% of operational days over European targets." Arnold assigned the problem to the Signal Corps Engineering Laboratories at Fort Monmouth, New Jersey. Lieutenant Colonel William L. Bayer, Chief of the Radar Development Section, received authorization to develop an airborne radar system capable of detecting other aircraft at ranges sufficient for formation flying. Bayer, who had helped develop the SCR-527 ground radar, understood the technical challenge immediately. Existing radar systems weighed several tons, required large antennas, and consumed power exceeding any aircraft's electrical capacity. Miniaturizing these systems while maintaining useful range seemed impossible given the technology available in October 1941. Bayer assembled a team of 11 engineers, including Dr. Luis Alvarez from the MIT Radiation Laboratory and Robert Baderi, a specialist in high-frequency electronics. The team began with a fundamental question: what minimum capability would allow formation flying in clouds? They calculated that detecting aircraft at 5 kilometers range with sufficient accuracy to maintain spacing of 100 yards would enable formations to hold positions safely. This specification drove every subsequent design decision. The breakthrough came from an unexpected source. In January 1942, the British provided technical data on their cavity magnetron, a device capable of generating high-power microwave radiation in compact form. The magnetron, developed at the University of Birmingham by John Randall and Harry Boot, produced 10 times more power than existing American magnetron designs, while weighing 1/10 as much. Alvarez recognized immediately that this technology made airborne intercept radar feasible. He proposed adapting the British magnetron for American production, combining it with American cathode ray tube displays and power supplies to create a complete system. The program received official designation in February 1942, SCR-717. The project's urgency escalated dramatically after America's entry into the war. General Ira Eaker, commander of the 8th Air Force in England, sent repeated requests for formation-keeping equipment. His crews were suffering 12% abort rates due to weather, with another 8% of bombers returning early after losing formation in clouds. Without reliable all-weather capability, strategic bombing effectiveness dropped by approximately 40% during winter months. Alvarez's team produced the first operational prototype in April 1942, just 4 months after receiving the British magnetron data. The system, designated AN, divided by APS-10, the military designation system changed during development, consisted of 5 major components. The magnetron transmitter generating 100 watts of pulsed microwave energy, a rotating antenna housed in a streamlined radome beneath the aircraft's nose, a receiver detecting reflected signals, a cathode ray tube display showing detected aircraft as bright spots, and a power supply converting the aircraft's 28-volt electrical system to the high voltages required by the radar. The revolutionary aspect wasn't any single component, but the system's complete integration. Previous airborne radar experiments mounted equipment designed for ground use, resulting in heavy, unreliable systems requiring constant maintenance. Alvarez's team designed every component specifically for airborne operation. The magnetron survived vibration and temperature extremes. The antenna rotated smoothly despite turbulence. The display remained readable in bright cockpit conditions. The power supply operated reliably despite voltage fluctuations. Total system weight, 63 pounds. Power consumption, 350 watts. Detection range, 8 kilometers for a B-17 size target. The system exceeded specifications in every category. Why couldn't Germans conceive of this approach? The answer lay in different design philosophies. German radar development emphasized maximum capability regardless of size or complexity. The Würzburg radar, Germany's most advanced system in 1942, provided exceptional accuracy and range, but required a trailer for transport, multiple operators, and extensive setup time. German engineers optimized for performance, assuming that if airborne radar became necessary, they would simply miniaturize ground systems. This approach underestimated the difficulty of miniaturization, while overestimating the time available for development. American engineers, by contrast, optimized for production and reliability from the beginning. Alvarez insisted every component be manufacturable using existing industrial processes. No exotic materials, no handcrafted components, no techniques requiring specialized skills. The magnetron used standard copper. The cathode ray tube employed commercial glass. The antenna rotated on standard ball bearings. This philosophy of good enough for mass production enabled rapid scaling from prototype to production quantities. The transition from working prototype to mass production occurred with speed that would have seemed impossible to German planners. In May 1942, The War Production Board authorized production of the AN divided by APS-10 system under the designation SCR-717. The system carried multiple designations during development, creating confusion in German intelligence assessments that tracked different designation systems. The Western Electric Company received the primary contract, with production facilities established at Baltimore, Maryland, Kearney, New Jersey, and Burlington, Massachusetts. By December 1942, just 7 months after the prototype's first flight test, Western Electric had delivered 312 complete radar systems. By June 1943, monthly production reached 675 units. By December 1943, production peaked at 1,200 units per month. Total wartime production exceeded 17,000 sets, with the AN divided by APS-10 and its improved successor, the AN divided by APS-13, equipping nearly every American heavy bomber deployed to Europe. These production numbers reflected industrial capability that German analysts consistently underestimated. The SCR-717 program employed 47,000 workers across 138 facilities. Western Electric operated the final assembly plants, but component production distributed across an extensive network of subcontractors. The magnetron came from Raytheon Manufacturing Company in Waltham, Massachusetts, which produced 8,000 units monthly at peak production. The cathode ray tubes came from L&B, Dumont Laboratories in Passaic, New Jersey, producing 12,000 display tubes monthly. Antenna assemblies came from 13 different machine shops across Pennsylvania and Ohio. Power supplies came from 23 different electronics manufacturers. The cost per unit, including installation and training, totaled approximately $9,800 in 1943. The entire program cost exceeded $166 million by war's end, making it the fourth largest military electronics program after radar proximity fuses, the proximity fuse program for anti-aircraft artillery and military radio production. For context, this expenditure exceeded Germany's total radar production budget for 1943 by a factor of 3.5. The comparison to German radar production reveals the industrial gap that Wehrmacht intelligence consistently failed to grasp. Germany's entire radar production for 1943 totaled approximately 8,000 units of all types: ground-based systems, naval radars, airborne intercept radars, and fire control systems combined. The United States produced 17,000 airborne formation-keeping radars alone, plus thousands of additional radar systems for other applications. A single American radar program outproduced Germany's entire radar industry by more than 2-to-1. The disparity extended beyond simple production numbers to industrial organization. German radar production concentrated in a few large facilities, primarily Telefunken's Berlin plant and Lawrence AG's factories in central Germany. This concentration made production vulnerable to strategic bombing and limited production expansion. American production distributed across 138 facilities in 38 states, creating redundancy that prevented any single bottleneck from halting production. When a fire destroyed part of Raytheon's magnetron production facility in August 1943, production dropped by only 12% for 6 weeks before returning to normal levels. Alternative suppliers absorbed the shortfall. Worker demographics revealed another advantage that contradicted Nazi racial ideology. The Western Electric Baltimore facility employed 18,700 workers, including 7,200 women, approximately 39% of the workforce. African Americans comprised 1,400 workers, approximately 7.5%. Disabled workers, including 320 veterans from the First World War, made up approximately 1.7% of the workforce. These inferior populations, according to Nazi racial theory, were outproducing the German master race by factors exceeding 3-to-1. The The training infrastructure supporting this production demonstrated systematic American advantages. Western Electric operated 3 training centers, teaching radar maintenance and operation. The Signal Corps operated 8 additional schools, training military personnel in radar employment. Training throughput exceeded 2,000 personnel monthly by mid-1943. Germany's comparable training programs, limited by both equipment availability and instructor shortages, produced fewer than 400 radar specialists monthly across all services. The production statistics revealed not just quantitative superiority but fundamentally different approaches to industrial warfare. Americans designed systems for mass production, employed diverse workforces efficiently, distributed production to prevent bottlenecks, and scaled training to match equipment deployment. Germans designed superior individual systems, concentrated production in vulnerable locations, limited workforce participation based on ideology, and struggled to scale training. The result: America fielded 17,000 airborne radars, while Germany fielded 8,000 radars of all types total. The AN divided by APS-10 entered combat service with the 91st Bomb Group, flying from Bassingbourn, England, in June 1943. Lieutenant Colonel Clemens Wurzbach, the group's commanding officer, initially approached the new equipment with skepticism. His crews had trained for months on visual formation flying, perfecting the techniques needed to maintain the tight defensive boxes that concentrated firepower against German fighters. Adding electronic equipment seemed like unnecessary complexity that might distract crews from fundamental flying skills. The first combat test occurred June 13, 1943, during a mission to Bremen, Germany. Weather forecasters predicted solid cloud cover from 5,000 to 22,000 feet over the North Sea and northern Germany, with icing conditions above 14,000 feet. Under normal circumstances, such weather would have forced mission cancellation. Instead, Wurzbach led 18 B-17s, each equipped with AN divided by APS-10 radar, into clouds at 8,000 feet over the English coast. The formation maintained perfect integrity through 73 miles of instrument conditions, emerged from clouds 12 miles from the initial point, and completed the bomb run with all aircraft in position. Not a single bomber aborted due to lost formation. The mission demonstrated conclusively that radar-guided formation flying worked under operational conditions. Tactical doctrine evolved rapidly through repeated combat experience. Initially, bombardiers operated the radar, monitoring neighboring aircraft, while managing navigation duties. This arrangement proved unsatisfactory during combat, when bombardiers needed to focus exclusively on the bomb run. By August 1943, most groups assigned radar monitoring to the navigator, who called out position corrections to the pilot. This arrangement worked better, but still divided the navigator's attention between position keeping and primary navigation duties. The optimal solution emerged from the 305th Bomb Group operating from Chelveston, England. Colonel Curtis LeMay, the group commander who would later direct the strategic bombing campaign against Japan, assigned dedicated radar operators from among crew members with electronics training. These operators, usually the radio operator or spare crewman, monitor the radar display continuously during formation flight, calling out position corrections and alerting the pilot to nearby aircraft. This arrangement freed the navigator for primary duties while ensuring constant radar monitoring. LeMay's tactical innovation became standard procedure across the 8th Air Force by October 1943. The equipment enabled formation tactics impossible with visual flying alone. The standard B-17 combat box placed 18 aircraft in tight defensive formation, with vertical separation of only 150 feet between layers and horizontal separation of 100 yards between aircraft in the same layer. Maintaining this spacing in clouds using instruments alone would have been impossible, Pilots couldn't judge distance accurately enough. Radar provided precise ranging, allowing pilots to hold position within 50 feet even in solid clouds. The result? Formations maintained defensive integrity regardless of weather, drastically reducing vulnerability to fighter attack. Combat effectiveness statistics demonstrated the tactical advantage. During the first 3 months after AN divided by APS-10 deployment, the 91st Bomb Group's mission completion rate increased from 72% to 89%. Aircraft losses to mid-air collisions dropped from 0.8% per mission to 0.1%. Formation integrity after emerging from clouds improved dramatically. Groups equipped with radar achieved 93% of bombers in proper position, compared to 67% for groups without radar. The statistics spoke clearly. Radar-equipped formations flew more missions, suffered fewer losses, and delivered bombs with greater concentration. The 306 Bomb Group, operating from Thurley, England, demonstrated the system's capabilities during the Second Schweinfurt Raid, October 14, 1943. Weather conditions over the target included scattered clouds at 14,000 feet and solid overcast at 18,000 feet. The lead bomber, piloted by Captain Robert Morgan, used radar to guide the formation through cloud layers during the bomb run. The group achieved the mission's highest bombing accuracy, placing 73% of bombs within 1,000 feet of the aiming point, despite cloud interference with visual sighting. Post-mission analysis credited radar navigation for maintaining formation integrity through clouds that would have scattered formations attempting visual flight. By January 1944, AN divided by APS-10 equipped virtually every B-17 and B-24 operating from England. The 5th Bombardment Wing, controlling 3 bomb groups totaling 135 bombers, achieved mission completion rates exceeding 92% even during winter weather. The 8th Air Force as a whole flew an average of 327 effective bomber sorties daily during January and February 1944, compared to 193 daily sorties during the same period in 1943 before widespread radar deployment. The operational tempo nearly doubled, primarily because weather no longer grounded missions. The tactical employment of formation-keeping radar demonstrated that technology alone doesn't determine battlefield effectiveness. Proper integration of technology with tactics and training creates operational advantage. The AN divided by APS-10 provided capability, but American operational doctrine exploited that capability systematically. Specialized crew positions for radar operators, modified formation tactics, optimizing radar coverage, training programs ensuring crew proficiency, and leadership willing to trust electronics over traditional visual methods, all these factors combined to transform technological capability into tactical dominance. The true impact of radar-guided formation flying became apparent during Big Week, February 20th through 25th, 1944, when the 8th Air Force launched its concentrated offensive against German aircraft production facilities. Weather conditions during these 6 days exemplified Northern European winter. Cloud cover from ground level to 25,000 feet, icing conditions throughout, visibility less than 1 mile at most altitudes, and scattered thunderstorms, adding severe turbulence. Under 1943 conditions, such weather would have allowed perhaps 2 missions during the entire week. Instead, radar-equipped formations flew 6 major missions involving over 3,000 bomber sorties. The first Big Week mission, February 20th, targeted aircraft factories at Leipzig with 298 B-17s from the 1st Bomb Division. The formation assembled in solid clouds over England, flew 470 miles to the target through instrument conditions, and maintained sufficient integrity to achieve concentration of bombs despite clouds obscuring the target during the actual attack. German fighters, expecting weather to prevent missions, had dispersed to satellite fields for maintenance. The Luftwaffe managed only sporadic interceptions, shooting down 21 bombers, a loss rate of 7.1%, high by later standards, but acceptable given the target's importance. Without radar formation keeping, the mission would have been impossible. The impact on German fighter defenses was systematic and devastating. General Joseph Schmid, commanding Luftwaffe Fighter Corps once responsible for defending Western Germany, reported to Reichsmarschall Goering on February 23rd. American formations now maintain cohesion through weather conditions that ground our own bombers. Our defensive doctrine assumes weather provides protection when visibility drops below operational minimums. Americans ignore weather entirely. We cannot defend if Americans can attack regardless of conditions. Schmid's assessment identified the strategic problem accurately. German air defense relied on using weather to restrict enemy operations. When Americans flew through weather that grounded German fighters, the entire defensive system lost effectiveness. The second critical engagement, demonstrating radar's impact, occurred during the March 4, 1944, raid on Berlin. Weather over the target included 10/10ths cloud cover from 8,000 to 27,000 feet, with tops extending above the bomber's operational ceiling. The force of 658 B-17s and B-24s flew the entire mission on instruments, with lead bombardiers using H-2X ground mapping radar for the bomb run. Defensive formations maintained integrity throughout, despite never having visual reference to other aircraft. The Luftwaffe, assuming clouds would break up formations and create opportunities for isolated attacks, launched 400 fighters. Instead, they found unbroken defensive boxes bristling with over 50 machine guns per box. German fighters shot down 69 bombers, a loss rate of 10.5%, but German losses totaled 66 fighters destroyed and another 93 damaged, unsustainable attrition for a defending force. The reversal in Luftwaffe assessment of American capabilities proceeded through clear stages documented in captured intelligence reports. The earliest assessment, from April 1943, dismissed American electronic warfare capabilities. Quote, American formations demonstrate poor cohesion in adverse weather. Electronic aids appear experimental and unreliable. German air defense retains significant advantage when weather restricts visibility. By August 1943, the tone had shifted to concern. American bomber formations maintain integrity through weather conditions previously considered operationally prohibitive. Electronic assistance suspected, but capabilities uncertain. Defensive doctrine requires revision to account for all-weather American operations. By December 1943, assessment turned to alarm. American formation-keeping capabilities exceed German expectations. Electronic navigation and formation aids enable attacks through weather conditions German bombers cannot safely navigate. Strategic implication: weather no longer provides defensive advantage. The final assessment, dated March 1944, acknowledged the revolution. Americans possess systematic all-weather bombing capability through electronic navigation aids, deployed universally across heavy bomber fleet. German defensive doctrine based on weather restriction is obsolete. Americans will attack regardless of weather conditions. No defensive counter available. The psychological impact on Luftwaffe pilots was profound. Major Johannes Steinhoff, commander of Jagdgeschwader 77, described the change in his post-war memoir. In 1942 and early 1943, we welcomed bad weather. Clouds meant the Americans stayed home or scattered, providing easy pickings. By summer 1943, we realized weather didn't protect us anymore. The bomber boxes appeared from clouds perfectly formed, flying through conditions where we couldn't see our own wingtips. The psychological effect was worse than the tactical impact. We felt hunted, even when weather should have grounded all flying. Tactical adaptations attempted by the Luftwaffe demonstrated recognition of the changed situation but failed to counter American capabilities effectively. In September 1943, Fighter Corps 1 implemented standing patrols above cloud layers, attempting to intercept Americans as they climbed out of weather. This tactic failed because radar-equipped formations could navigate to assembly points within clouds, emerging only when all aircraft were in position. German fighters waited above clouds while Americans assembled beneath them. In November 1943, the Luftwaffe attempted mass attacks through clouds, hoping to break up formations before defensive integrity solidified. This approach resulted in catastrophic German losses. Pilots lost their own formation integrity while attempting to break up American formations that held together effortlessly. The Luftwaffe abandoned the tactic after losing 73 fighters in 3 missions without achieving decisive disruption of American formations. By January 1944, the Luftwaffe essentially conceded all-weather air superiority. Defensive operations concentrated on clear weather interceptions, accepting that cloudy weather meant uncontested American operations. This concession represented complete reversal from 1943 doctrine, when German planners expected weather to limit American operations to perhaps 1/3 of potential mission days. The comparative effectiveness statistics demonstrated the transformation. During the first quarter of 1943, before widespread radar deployment, the 8th Air Force flew an average of 193 effective bomber sorties daily, with mission completion rates of 74% and weather-related aborts exceeding 14%. During the first quarter of 1944, after universal radar deployment, effective bomber sorties averaged 347 daily. Mission completion rates reached 91%, and weather-related aborts dropped to 3.2%. The operational tempo nearly doubled, while reliability increased dramatically. The strategic impact extended beyond simple sortie counts to fundamental changes in targeting and campaign planning. Radar-equipped formations could strike any target, regardless of weather, enabling year-round pressure on German war production. The combined bomber offensive, the systematic campaign against German industry, became viable only after radar eliminated weather restrictions. Without all-weather capability, strategic bombing would have remained intermittent and unpredictable, allowing German industry time to repair damage between attacks. The systematic failure of German intelligence to understand American radar capabilities until too late represented more than tactical oversight. It reflected fundamental misunderstanding of American industrial philosophy. Post-war interrogations of German technical intelligence officers revealed the depth of this miscalculation. Colonel Joseph Kammhuber, architect of Germany's air defense system, reflected in a 1946 Allied interrogation. "We knew the Americans possessed radar technology comparable to ours. We saw the equipment in crashed bombers. What we failed to understand was their willingness to install such complex systems in every aircraft. German doctrine reserved radar for specialized roles: night fighters, fire control, key ground installations. We calculated that equipping every bomber with radar would exceed any rational cost-benefit analysis. The Americans proved that, in industrial warfare, rational cost-benefit analysis is irrelevant if you possess overwhelming production capacity." Major Wilhelm Specht, who led the technical investigation into American airborne radar, elaborated in a 1947 interview. "The fundamental error was assuming Americans thought like us. We believed radar was too valuable, too complex, too expensive to deploy universally. We would have concentrated such technology in specialized units, maximizing effectiveness while controlling costs. Americans built it into every single bomber, treating sophisticated electronics as casually as we treated radios. This wasn't better technology. This was an entirely different philosophy of warfare. The recognition extended to tactical implications that German commanders acknowledged only after experiencing them in combat. General Adolf Galland, commander of German fighter forces from November 1941 through January 1945, reflected in his 1954 memoir, The First and the Last. By 1944, weather had become our enemy rather than our protection. Every day with solid cloud cover meant American bombers over Germany, with our fighters grounded or flying blind while they maintained perfect formations through clouds. The Americans had turned our defensive advantage into our greatest vulnerability. We couldn't see them, couldn't find them in clouds, couldn't intercept them systematically. When weather grounded us, they flew with impunity. Post-war analysis by German military historians emphasized the strategic significance. The official Luftwaffe history, completed in 1953, concluded, American all-weather bombing capability, achieved through universal deployment of formation-keeping radar, represented the decisive factor enabling sustained strategic bombing. Without this capability, German industry would have had sufficient time between attacks to maintain production despite bombing. With all-weather operations, Americans achieved cumulative effects that overwhelmed repair capacity and ultimately destroyed German war production. The long-term influence on warfare extended far beyond World War II. The AN divided by APS-10 established the principle that every aircraft in a formation requires independent navigation and position-keeping capability. Modern military aviation universally adopts this approach. Every aircraft in contemporary formations carries GPS receivers, transponders, and data link systems, enabling precise formation flying under any conditions. The specific technology has evolved, but the fundamental concept remains unchanged. Distribute capability to every platform, rather than concentrating it in specialized units. The broader lesson concerned industrial philosophy and strategic capability. American willingness to deploy sophisticated technology universally, rather than concentrating it in elite units, reflected fundamentally democratic assumptions about warfare. German military doctrine, rooted in aristocratic traditions, emphasized elite forces using specialized equipment. American doctrine emphasized universal capability, accepting higher per-unit costs to achieve flexibility and sustainability. In industrial warfare, fought over years, the American approach proved decisively superior. The radar story also demonstrated that technical sophistication without production capacity provides limited advantage. Germany maintained technical parity with Allied radar development throughout the war. In some respects, German radar technology led Allied efforts until 1944. But German inability to translate technical knowledge into mass production meant sophisticated designs remained experimental, while American equals good enough technology equipped thousands of aircraft. In warfare, adequate technology deployed universally defeats superior technology deployed rarely. The irony that African American workers, considered racially inferior by Nazi ideology, contributed substantially to the radar production that defeated Germany adds philosophical weight to the technical achievement. The Baltimore Western Electric Facilities workforce demographics, 39% women, 7.5% African American, nearly 2% disabled, demonstrated that democratic societies mobilize human potential more effectively than authoritarian systems based on exclusion. The equals master race lost to a diverse coalition that recognized talent regardless of gender, race, or physical limitation. What began with Major Herman staring at incomprehensible formation precision on radar screens in March 1943 ended with complete Allied air superiority by summer 1944. The Wehrmacht's mockery of American radar technology dismissed as too complex, too expensive, tactically irrelevant, transformed into desperate recognition that weather no longer protected Germany. The clouds that should have been Germany's ally became America's advantage. Every storm system, another opportunity for uncontested bombing rather than protective cover. The lesson transcended World War II. Industrial democracies possess systematic advantages in long wars requiring sustained production. American willingness to equip every bomber with sophisticated electronics, train every crew in radar operation, and build production infrastructure supporting universal deployment reflected values fundamentally incompatible with authoritarian efficiency. The Germans optimized for elite performance. The Americans optimized for universal capability. History rendered its verdict through the rubble of German cities destroyed by bombers flying through clouds Germany thought would protect them. General Galland's final assessment from his 1985 interview captured the transformation most succinctly. Equals, we saw their radar equipment and laughed. Too heavy, too complex, too expensive to be practical. We were the impractical ones. They were building the future of warfare, while we clung to the past. Every time weather closed in and we heard bomber engines in the clouds above, we understood again that we had lost before the first bomb fell. They had industrialized precision bombing, turned strategic air warfare into a factory operation that ran regardless of weather. We had no counter to that. How do you defend against an enemy who attacks through the weather itself?